Hello and welcome to the third part of my lecture series about stability. In this part, we are going to characterize some minimal submanifold of the sphere by their index and nullity. I recall just that the second part we present some examples, mainly great spheres and Clifford hypersurface, and we computed their index and nullity. This talk is divided in three parts. We will first present the classical results of Simon, in which the great spheres are characterized by their index and nullity. Then the second part we will present a result by Urbano about the characterization of the Clifford torus in the three spheres by their index, and also some generalizations in higher codimension. And finally, we will present the present situation of the study of lowest index examples in the three spheres. Okay, so the first main result is by James Simons in the 60s, and it says the following. If we consider an isometric minimal immersion of a compact manifold M in the sphere of dimension M, then we've got these two possibilities. First, the index of the immersion is always greater or equal than the codimension, that is, there is no stable compact minimal submanifolds in the sphere, because the index is always positive, and the equality in this inequality holds if and only if phi is actually an embedding and the image is actually a great sphere. So great spheres are not stable, but they are the lowest index examples among all the minimal immersions. And also Simons characterized also the sphere by their nullity. So the nullity of a minimal immersion is always bigger or equal than the codimension times dimension plus 1, and the equality holds only in the case of a Greek sphere. I just recall this picture that shows in the lowest dimension examples, we are in S2, and we consider a minimal immersion, which is in this case is an equator. Then we actually see that we can deform the equator, decreasing the volume, so the equators are actually not stable. Okay, so we are just going to give some sketch of the proof, some ideas how to solve this result. So first we claim that minus d, minus the dimension of the minimal immersion, is always an eigenvalue of the Jacobi operator, and then that the multiplicity of this eigenvalue is precisely the codimension when the immersion is a great sphere, or the multiplicity is actually bigger or equal than m plus 1, the dimension of the ambient sphere plus 1. Okay, so we consider for proving this claim, we are going to consider our M sphere inside the Euclidean space, with second fundamental form given by the product of VW by the metric in the direction of P, which is the normal direction in the Euclidean space. And then we are going to use as test section in our for our Jacobi operator, the orthogonal component of fixed vector field in the Euclidean space. So if I take a fixed vector field in the Euclidean space, we can orthogonally decompose as a tangent component to the manifold, normal component to the manifold in red, and normal component to the sphere in the Euclidean space. So it's a direct computation to see that if we consider as normal section the normal component of these fixed vector fields in the Euclidean space, then they are actually eigensection of the Jacobi operator, and its associated eigenvalue is precisely minus d. So we actually get the first part of the claim. Okay, now we would like to study the multiplicity nu of this eigenvalue. So for that purpose, we are going to consider the following linear map F, which is just the projection over the orthogonal component to M of fixed vector fields. the multiplicity of minus d, we are going to call it nu, is actually bigger or equal than the dimension of the image of this linear map, which is the dimension of the origin space n+1 minus the dimension of the kernel. So either the kernel is 0, and so the multiplicity of nu is bigger or equal than n+1, in particular the index is bigger or equal than n+1, or the dimension of the kernel is actually d+1 and it is a sphere. Okay, and that will show the claim. So we are going to assume that actually the dimension of the kernel is bigger or equal than 1, since if it is 0, we get part of the claim. Okay, so in this case, we need to show that it is actually, this dimension of the kernel is actually d+1, and the immersion is actually a great sphere. Okay, so if there is a vector in the kernel, then there is an A which is not 0, such that its orthogonal component to the immersion is actually 0. In this particular case, since A is not 0, we've got this equality that the tangent component of A plus the A times phi in the direction of phi is a non-zero vector. If the component in the direction of phi is 0, then deriving we get that also the tangential component is 0, which is a contradiction. Hence, the function f defining the scalar at each point of M as the scalar product of A times the position vector is known as non-trivial function. And it is an easy computation to show that its Hessian is proportional to the metric. Okay? Then, thanks a result from Obata in the 60s, we get that actually these characterize spheres. So our manifold is actually isometric to a d-dimensional sphere. Now, if we look at the Gauss equation, we actually get that the length of the second fundamental form is 0. So it is phi is actually totally geodesic. That is, phi is actually a totally geodesic great sphere. In such case, it is easy to see that the dimension of the kernels is actually d+1. That shows the claim and proves the result of Simons. Okay, so now we are going to see another classical result, which is the characterization of the Clifford torus by its index. So this result is due to Urbano in the 90s and says the following. If we consider a compact oriental non-totally geodesic minimal surface in the 3 sphere, okay, so this result is only valid in dimension 3 for surfaces, then its index is strictly bigger than 5, and the equality holds if and only if the submanifold, the surface, is actually the Clifford torus. So sorry, because that strict inequality should be bigger or equal than. Okay. So it is an open problem to get a similar characterization for Clifford hypersurfaces, which is the generalization of Clifford torus to higher codimension. Okay, that kind of hypersurfaces were studied in the previous part of the talk, where we computed their index and nullity. However, there are partial answers. One of them is this result by Perdomo, where he characterized Clifford hypersurfaces by their index, but under the extra assumption of being antipodal invariant. So I posed the following conjecture is whether these Clifford hypersurfaces in general codimension without this extra hypothesis of being antipodal invariant are actually the only minimal hypersurfaces with this index. Okay, finally, we are going to say something about the present situation in the three-dimensional case, because it's the most studied and perhaps the most interesting one. So first, in 2010, Szabo gave a lower bound for the index of any minimal immersion in terms orientable in terms of the genus. So the index is always bigger or equal than 1/2 of the genus plus 4. But okay. So very recently, 2 years ago, Capuleas and Wigul computed the index of the Lawson's orientable minimal examples. So Lawson's produce orientable minimal examples for every genus in the 3 sphere, and they are denoted by psi G1, where G is the genus. Okay, and the index of this minimal example is actually twice the genus plus 3. Okay, so here I present some pictures of this, how this minimal surface looks like by Heller and Smith for genus 2, 3, 4, and 5. Okay, the pictures are done projecting stereographically the minimal surfaces in S3 to R3. Okay, so these examples are actually high symmetric, and it is reasonable to think that they are the index must be one of the lowest one of the surfaces apart from the sphere and the Clifford torus. So there is this conjecture that the first of the examples, the lowest genus 1, the genus 2 examples, is the only two-sided compact minimal surface of the 3 sphere, which index 7. So the situation in the 3 sphere is the following. For index 1, Simons characterized the great spheres, and the only one attained that value of the index. For index 5, Urbano characterized the Clifford torus. For index 6, there is no known examples of minimal surface with precisely this index, and for index 7, we already know that the Lawson example psi 21 has actually index 7, but we do not know if we can characterize that surface by its index, or there are actually more minimal surface with index 7. Okay, so this finished part 3 of my talk, and in the following one I will present some recent results jointly with Francisco Urbano concerning the index of stability of minimal submanifold, but in Berger sphere. Okay, thank you.